This week we deal with finite state machine and the computer model that we call the Neumann model. We studied combinational logic before. We went all the way up to functional units. I think I convinced you we could, at least in principle, build a functional unit that computes whatever we wanted to compute. We even had memory elements, so that seemed to help us to build a computer. We have data and we have operation. And the control part really comes in this week to help the von Neumann model to work. So let's visit this notion. Because we can build any logic from truth table, and that's how I convinced you we can build. We tried another as an example, but we can do other operations as we want. And we will probably use multiplexer to choose between different units when deciding what function to use, decoder and multiplexer for the output, and that's controlled by an operation code. This is sort of the beginning of what we see how to code a computer. But let's pause that question and say and think hard about really, is it any logic? What about very complex logic? What about if we want to detect a letter? And so that's easy. Okay, if we're detecting a letter to be A, we're really just testing the value to be the same as the code. Whatever is the code, we can use ASCII code for the simple example, but today maybe we use Unicode and whatnot. So that's really not that difficult, okay? But if you want to find out if a string contains letter, now what do? Well, it's a bit different, okay? In this case, let's assume it's a fixed length. What you can do, you can compare every letter to see if it is the letter that you're looking for. In parallel, you have a fixed number of letters, okay? Then you have a fixed number of circuits that simultaneously triple these. And you can even go through some encoding to find out where this really occurred at the first time. But the problem is, here's the example. Let's say we want to find a cat. And let's say we assume the input are encoded in ASCII code, which means C is really value 99. And if you do the binary coding, that's really what this is. And you can verify yourself that this is the circuit that detects the 8-bit correspond to decimal value 99. We can even use a simplified symbol to say that this is a giant AND gate. Some of the value are regular, others are inverted, and that's it. Okay, so we have we can abstract that away with a box. It's just testing if it's C. Let's say we want to be case insensitive. What we can test is for a different value, the capital letter C in this case, 67 decimal value, right? And you OR the result. Now you have a C detector. And if you want to detect cat, then you have to detect C, A, and P simultaneously, but that's only if the string appears, the word appears at the beginning of the string. So what if it's offset by 1 character? Now you have to have this. What if it's offset by 2 characters? So the idea is that if you try to detect in your input expanded in space a particular pattern, the logic is going to be very, very complex. We did this calculation. Suppose we go back to this whole thing, right? How many gates do we have? We have 7, 8, some inverters. Every NAND gate or every AND gate that we build is probably 4 transistors. You're talking about 30s of transistors. That's just one detection. And if you do case insensitive, you're making it 80s of transistors and so on. And you're duplicating this. So the number quickly expands. And the problem is not just a particular number. Oh, it's large. It's 200 transistors too many, or 5,000. The problem is, if we build it like this, it's only going to have one functionality, that is to detect the phrase cat. And so that's a problematic general approach. And we don't do this in real life by solving the problem in one go. And that's what a combinational logic does. You send all the input. At the end of all the gates, there is some output, some form of output, yes or no. Okay? But in reality, we kind of do this by step. Let's see the first letter. And if that's this, then we're gonna do the next step, see the next letter, so on and so forth, right? So that's what we do. Work on a part of it, keep track of the solution, remember where we are, and decide what the next step is. This kind of step-by-step approach implemented in a circuit is called a sequential logic circuit. Okay, that's to differentiate from the pure combinational logic circuit, which is not sequential. It's, if you ignore the time delay, it's instantaneous. You give me a input, I give you an output. Okay, so this is done using the memory element. Okay, here is one logic diagram. We started with a couple of we started with these states, right? If we see a C, we go to a different state, and you can sort of think about this state as having seen letter C. And then if you see A from that state, you move on to the next state of having seen state CA, and so on. So how do I represent state? Well, I give them different code. Starting state may be coded 0, 0. The C state may be coded 0, 1. Next state 1, 0. Whatever, it's your choice. Right? Everything is represented as numbers at the end of the day. And here's a circuit. You can have your combinational logic, but you also have some storage to track the state. And your state changes depending on what the input is, as well as what the current state is. And your output depends on, of course, what the state is and also what the current input is. And if you have those, you can solve the problem one by one. So for instance, the cat example that we gave, right? We look at the input and we look at the current state. And the state, since we have 3 states, 4 actually, we encode them with 2 bits. So now I introduce a state variable S01. It's a 2-bit bit vector. So now my condition is this. I have an input. Okay, I'm testing to see if it's C. And you remember that that was a whole bunch of AND gates, inverters, and so on. So that gives me one condition, yes or no. And then I'm going to end it with another test, which is the state currently 0? If this is true and that is true, then my new state is going to be 1. And so on. I can tell what each state is. And that's encoded in this combinational logic. I take the state, I take the input, here's my old state, here's the input, and then I decide what my new state is. All of that can be written down in a truth table, so this combinational logic, we got it handled. Okay, and where does the new state goes? Well, it's fed into the 2-bit storage. That stores what the current state is. And if we work this out, it will basically carry out the diagram of this state transition that we wanted. Okay, of course, if you're careful about this, I'm not doing a good job in the exact thing. This isn't going to test CAT because it's only going to test CAT if you see CAT in a sequence. It doesn't react properly if you have letters such as C, CAT. We have to write the complete logic. So that's beyond the point, right? The point is I can write some state transition logic. This one over here is not completely correct to detect CAT, but we can write it out, and it's going to be translatable to a truth table, and we can implement it. So we need to know about the storage, because this matters. Why? Because at the current state, I am checking I need the state both as an input and also as the output of something. This is a feedback loop that if you don't handle well can be problematic, right? I'm using my input, but the input is simultaneously my output. So you need to manage the storage correctly. And that introduces this type of register. Okay? It's two stages. As you can see, I have a D latch here. This is my first D latch. It's controlled by, the right enable is controlled by what we call a clock signal. And we send its invert to a second stage. So this is the master stage and that's the slave stage. And what does that do? Well, if you look at a clock signal, usually it's like that, equal amount of time in high and low. And the entire period is called a clock cycle. And we can see that at any moment, only one of the stages is activated in the sense of latching new data. If clock is high, the master is latching the data. D latch is working, Q is going to follow D, and when the clock signal is low, that's going to stop. The master is going to stop, not do anything, and the slave is starting to work. Okay, so remember D latch, the function diagram can be written as such. When WE is 0, the Q is just the old Q. Doesn't matter what D is. When it's 1, it tries to follow D. So if we expand this out to have the Q master and slave written out, we see that when the clock is high, the slave part is still showing whatever it is prior to clock being 1. But the master is latching to the input of D. Okay, and then when the clock transitions to 0, the master is going to stay put, and it's not going to change to D. Now you can change your D, but whatever gets latched into the slave is Q master. No longer, it's isolated from D. Okay, so this is also called a flip-flop. It's controlled by a lock. And usually you have many of these in the system that they're all controlled by the same clock, so they are synchronously latching the same data. Okay, and so terminology wise, when it's controlled by a clock, we tend to call it a latch. When it's not controlled by a clock, it's called a latch, and when it's controlled by a clock, it's called a flip-flop. Here's one very simple example of a logic that only adds 1 to the state. So your state is nothing but a counter. Okay, it starts with 0 and it goes to 1, 2, 3, and so on and so forth. And let's assume we have enough bits to handle this. So here I have 1 bit. This is a master slave flip-flop. Okay, this may be bit 0. I have a bit 1 over there and bit 2 over there and so on. So I can look at the data that comes out as not just a bit, but every bit comes out into, a bundle of signals. So I can treat this as an m-bit input. Okay, and I have an add 1. This is pure combinational logic. So if you give me n, what comes out is n plus 1. And the diagram down here, over here, is just trying to show you how this all works out. Okay, so we have to follow this. It's basically everybody is having some input. Okay, if I can control this, it's not that difficult. We can start anywhere we want, but let's start when we assume the Q is 0. Right now, at the beginning of, at this time point, before this time point, let's assume the state stored, the counter, is 0. So Q slave is a 0. Now, this Q slave here is what happens in a register, okay, in multi-bit, not just one flip-flop. So it can be bit 0 is 0, bit 1 is 0, bit 2 is 0, and all of that. And then we simplify it to say, okay, then the value is 0. Okay, and we don't know which bit is high or low given a particular thing. So we just say, okay, some can be high, some can be low. Of course, if the value is actually 0, then all bits are low, but you get the point. Now, if we start this, we can look at the circuit. Suppose we're just, at time 0, right after time 0, and the clock is currently 1. What happens? Okay, you can follow this and say, well, Q we assumed that's 0. So here we have a 0 over here, and that's already stable. This is a combinational logic. So what comes out of it is a 1. And this 1, guess what's going to happen? Well, it's attached to the D port of my D latch with the clock being 1 now. So the Q is going to follow that. Whatever the Q used to be, we don't care. Beyond this, before this point, we don't care. This area shaded, we don't care. Okay, so D, we know that it's going to be 1. And Q follows D because write enable for the master is 1 over here. So Q is going to be 1. And this state is going to last until the clock turns to 0 at this point. Okay, at that point, what happens? At that point, the only thing that is happening is really Q slave. Or actually, the first thing that happens, I'm sorry, is Q slave. Okay, if I can try to simplify this one more time by clearing it, we're at this junction now, right? Because clock changed to low and write enable for the slave stage is just the invert of clock, write enable becomes high. And therefore Q slave will immediately latch the data of its D, which is the output of Q master. And since Q master is 1 at this point, we know that after some delay, this is what we mean by, so some bit may change from 0 to 1, others may change from 1 to 0, but after some settling time, it's going to be 1. The output is going to be 1. The Q slave, don't forget, is again fed into this combinational logic. So there's a 1 value, 0, 0, 0, 1. This value comes in. What do you think goes out? Well, after some circuit delay, its output is going to be 2. So I sort of showed that. Again, I have to clean this up. You see that there is a time delay, a little bit of a delay. D, after some circuit delay, is going to show up as 2. But this 2 is not going to impact the master stage. Why? Because at this point, the master stage's write enable is low. So the only time that it will affect the master stage is when it transitions back to master stage, clock being 1. And that's, again, after some delay, master, the Q of master stage is going to show up as 2. Okay, and this will repeat. This 2 is going to be latched into the Q slave when its write enable goes up, which is when the clock signal goes too low, and so on and so forth ad infinitum. This is how it works. So we turn the circuit on, we send clock. Every clock cycle, the system moves one step forward. And that's what we call a finite state machine. Or at least it's trying to implement an abstract concept that we call a finite state machine. So what is a finite state machine? Okay, if we look at a combinational circuit, it's sort of the way that we talk about it, it always has a finite number of input, a finite number of output, and a specification, a complete specification of what's going to be your output given a particular input. Okay, so you can think about it as truth table. 111 gives you, output 0. 110 gives you output 1, and so on. Well, a finite state machine has a bit more than that. It also has a finite number of external input and output. That's the same. But in addition, we introduce a notion that's along sort of the time domain. There is a finite number of states. Okay, at any time it's in one state, and the way this is encoded is a number, and because we know what the number is, and that becomes an internal input. So your actual output no longer just depends on the external input, which is here, the external input, but also the internal input, which is the state. In my example over here, 2 bits. Similarly, the output, similarly the state, the next state also depends both on the current state and the input. And all that state transition is specified. Given the input and the current state, what's the next state? That's state transition. That specifies the next state. And there is also the output, the external output. Given the current state and the current input, what is the output? And that's also completely determined. So if you have these components, by introducing the notion of state, we turn a simple combinational logic into a sequential logic, and it acts all like a finite state machine. Okay. In theory, of course, we can build any finite state machine, any single purpose finite state machine. Okay, the thing that we were showing, the search for cat, is a finite state machine. We can build that. But again, this is implemented with sequential logic, combination logic plus memory element, right? The abstract concept, I can draw it's called a finite state machine. Okay, not to be confused with flying spaghetti monster, of course. I can draw a finite state machine. I can write a finite state machine in C code or in Python. It doesn't have to be implemented by circuit. Okay, so that's a more general finite state machine. Is a general concept. Sequential logic is what you can do with gates and memory, and of course what it implements can be described as the finite state machine. And if we have these single purpose finite state machine, that's cool, that's fine, we do stuff, but what we wanted is to be able to change the behavior of that finite state machine, that it's not a single purpose, it's a programmable, controllable, configurable finite state machine. And that is what a von Neumann computer is. So most electronic system today nowadays really involves some form of computation, and it usually uses a general purpose computer, and it has memory and a processor. The processor has some sort of functional unit. It does arithmetics, and that's being controlled. The functional unit is being controlled by a control unit which reads from memory certain type of code. Okay, and that's what we call a computer. Of course, I'm just stereotyping guys and ladies. It's just a joke. Don't take it personally. So from this finite state machine, we can have, again, dedicated ones, but we want a general purpose kit. Okay, we want something that allows us to build any finite state machine as we see fit. And so the question that I ask is, how does that differ from an IKEA self-assembly furniture? You got components, you got your kit over here, right? And how do you put it into some functioning system? And the key thing is instruction. They have instructions. So let's talk about instructions. Okay, the finite state machine, known as the von Neumann, repeats this thing that I told you about already. It's really simple. Fetch the instruction and execute it. And rinse and repeat. Every time you fetch the next instruction. Okay? So if you implement something like that, you need to have memory, you need to have the code someone wrote in the memory, and the machine is going to go to some memory location, fetch the first instruction, execute it, and then go to the next memory location, fetch that and execute it, and so on and so forth. And that's what a von Neumann machine does. Now, that's oversimplification because it also involves some input things and some output things. Otherwise, how do we get our program into the memory to begin with? And if we computed something, how do we even get the result out to be meaningful? So we have that. But if we forget about the input and output for a moment, there is something that's vitally useful, important, and that's the program counter. Again, it's called a program counter by some historical incident. What it really does is to point you to the next instruction. So it's more of a instruction pointer, next instruction pointer. But never mind. We get stuck with PC, so let's just call it PC. A lot of the places, it's so embedded into the name. It's not, PC is really program counter. It's not a counter, but let's call it PC anyways. PC gives you the address. You go to the memory, okay, and we will see there is one such thing as a memory address register. Put your PC there. What do you get? The memory will work. It is controlled by a finite state machine, and it will go to the right location, get your data, put it into the data register. And now, what you do is you take that. It's a piece of data, but it's a special type of data. What is it? It's pointed to by a PC, so it's treated as an instruction. You put it into the instruction register, okay, the IR, and you act based on what that instruction says, and from there on. Okay, so now we have this general notion, okay, it's some instruction and stuff. So what type? What should these instructions roughly look like? Well, we can think about it. We do computation, right? So we'll do add, subtract, stuff like that. Okay. So that's easy. And you need an opcode, right? 001 for add, 010 for multiplication, whatever. You need something. But then what operands? Where do you put them? And in fact, how much space do you need to put these operands? So if you think about a digital photo today, 10 megapixel, what does that mean? It's 10 million pixels. What's a pixel? Pixel is a picture element, pixel. So that is one dot in your matrix of colored dots. Okay, in today's world, I mean, it's RGB, at least a byte for each. So just one digital picture is something in its expanded format, not compressed. We're talking about tens of megabytes. So that's a lot of storage. Okay. So a modern kind of computer, if you don't have that, it's going to be a pain in the neck to process an image. So that's why, if you think about your DRAM, your main memory, we're already using gigabytes of data. Okay, fine. We have gigabytes of data. So let's imagine having something like A equal B plus C. So where do you put these A's and B's and C? They're going to be in the memory. And how do you identify them? Right? Well, you identify them by using an address. If you have, let's say, for sake of round numbers, we have a 4 gigabyte memory, how many bits? That's 32 bits. So if you want to specify an operation that uses 4 gigabyte, you need 32 bits to specify one operand. And if it's A plus B goes into C, and that's how many bits you need. Plus, you need something to tell what the operation is. If you have 2 operations, 1 bit is enough, that kind of thing. So before long, you will see this is a very long thing. To tell the computer to do one thing requires about 100 bits, okay, which may not sound much to you, but it's a lot. It's not very efficient. And that brings us to a concept that we use a lot, which is the registers. Okay, what are they? Well, it's broadly speaking, it's just a group of storage together. It represents one number. Okay, and inside the processor we have lots of these. Why? To put your temporary variables. It's storage. Okay, stores the set of data that you're working on, the working set. You can make it much smaller. You don't have to put everything in it. Okay? You can clear it out from time to time and get new things in. And there are a couple of benefits. Okay, they're smaller, so you don't need a lot of bits to address them, to identify them. They're smaller and therefore faster. They're smaller, so we can put them on chip next to the CPU. Or inside the CPU, really. So they're not too difficult to access. So it's not slow. Okay. And this is what we figured out. Okay, it's a very long story how we got here, but we eventually figured out the best way is to work off register almost exclusively. So you're not even allowed to operate any function using data from memory. No. You bring your data from memory into registers, and then you operate off the registers. Okay, that's pros and cons, but let's just skip all of that to say that's what we're going to design. So the computer we're going to need will have these elements. It will have computational instructions. You have to be able to tell the computer to do add, subtract, and so on. Now that we decide we can only use data from register to operate, then we have to have a means of putting those value into the registers to begin with. And if we're done with them, we have to be able to send them out to free up the space. So those type of memory instructions are usually called load and store. Loads to move data from memory to register, store the other way around, sending data from a register back into memory. Here's the question, if you weren't there, is that enough? According to your coding, is that enough? And the answer is no. How do we write conditional statement? How do we write loops? And that is control instructions. Okay. So here's how you can imagine a regular instruction work. Let's start with the simple ones. We'll get to memory instructions and control instructions later. So we have 3 types of instructions, but for all of them, they will have some kind of opcode to tell the computer. We're not designing the computer yet. We're just saying, if we were to design a computer, what do we need? We need instructions. Otherwise, we can't let human tell the computer what they want to do. So now we're just thinking what is needed to even have this set of instructions agreed upon by the hardware and people who code the hardware. Okay, so here's a very simple example, and we have the binary format of it and some kind of human readable mnemonic. We need some opcode to say we're doing operation type 1, operation type 2. Okay, type 1 is an add. It's going to take values, operands from some registers. Do the add, put the result into some other registers. Here is your stereotypical type of instruction with 3 operands. And you can loosely translate that into, okay, this is really adding register R4, R7, the content in the 4th register and the 7th register, put it into the 2nd register. So how many registers we have? Okay, we have a bunch. Okay, in this case, in my very specific example, since I only have 3 bits to identify them, I have 8 registers. So they're typically called R0 to R7, R for register. And then if we can wire the output port of the register to our ALU, remember this is the thing that we already designed, we already know how it works, and we can send the opcode here, then we're done. We have the result in and we have to feed it back. So the computer would look something like that to start with, but we're not done. For this to work, what do we have to do? To execute the instruction, the very first thing is what? We have to load the instruction. We have to get the instruction in from the memory. And that requires which element? If you remember it correctly, it's the PC. Okay, we need the instruction. And the instruction is going to be stored in this format that we see over here on chip, on the CPU, this dude over here. The way we get this, starting from the PC, which is an address. Okay, if the PC says 00001, it's the first element, or element 1 in your main memory, which may have, let's say, 1 billion memory. If your PC is 100000, okay, some large number, then it's somewhere down in the middle, right? So the PC tells me where the instruction is. I use that to go to the memory, load the content of that memory cell, memory element. Again, we don't call these M0, M1. It's just, we call this the address. We go there, we get it. Okay, you can imagine this being an array with the first element being 0, the next element being 1, and so on and so forth. The next one is 4 billion, so I'll just write 4G, and in fact -1, right? So that's my 4 gigabyte or 4 giga. Okay, let's say 4 gigabyte. And the address is therefore a 32-bit value if I have a 32-bit computer. And I will load my instruction in. Well, how wide is my instruction? Well, it depends. In my case, in the case that I'm drawing over here, that's 13 bits. Of course, that's not a 2's round number, so we might want to round it up to 16 bits to give us a little bit more freedom. So we may have 4 billion 16-bit words. Okay. Okay, so that wouldn't be a byte, that would be actually 8 gigabyte if we have a 32-bit computer. But we may have, as we'll later see, that we have a 16-bit computer. So then that would be from 0 to 653. No, 5. I think that's 64K. This is 2 raised to the 16th power minus 1. Okay, so we have that many memory elements. Every element is 16 bits long. We send the address, 16 bits. We get a value, 16 bit back, loaded into our register, and we know. We say, okay, we know. This field over here, bit whatever, is one source register. These bits are another source register. So it's very easy. We send this bit to the right place. Okay, source register ID to register file, opcode to the functional unit. We get the result. Where do we send it back? That's determined by the destination register. And we're done. So that's how the computer roughly works. So now let's go back and think about, okay, if we design this instruction set, we can sort of kind of make it work. And that's, the subject of next entire week. But here, let's think about the way to even construct these instructions. Okay, we talked about this earlier, which is what do we need, right? We need computation instructions. We need code to represent them. We need memory instructions, right? So let's start with some examples. An add is a perfectly good example of a computational instruction. Let's just throw in another one. Let's give the operand ID 001. We say that's an add. 0010, let's say it's an AND. And we can have more. Okay, fine, we're done. As an example, right? We're done with the computational type. What else do we need? Remember, we want to work off the register all the time, right? So we need memory access instruction. Fine, let's say we have a load. Now, how do we tell the computer where to go and load? We say, okay, we can use an address. Great. Where do we put the address? Okay, the address has to be in the register. We can't have the address in the memory itself, because then the load cannot specify. A load has to use register. Every instruction has to use registers. So the address has to be somewhere. Let's say it's in register 0, and we want the computer to take the value out of register 0, use it as an address to go to memory, grab whatever is in there, put the content into register 3. But hold on a second. We have a little problem, right? What's the problem? So load is the way for us to put data into register. But in order for load to work, we need address, which we want to put into registers. How do we do that? You say, oh, we can put the address into the memory. How do we get to that memory cell? No? Basically, how do we initialize anything? If we don't have a way to set up a register value to be something meaningful, we cannot do anything. Never mind if the entire program is there already in the main memory. So that's the problem we're dealing with. We need some way to initialize registers. And we cannot use memory to initialize the register, because that's a bootstrap problem. We cannot haul ourselves out of the mud using our bootstrap. We gotta use something else. It cannot be in the registers because, we have to initialize that first. And the only way left is really the instruction itself. The instruction is right here. Whatever is there can be used. And so that is the notion of immediate. We need to embed some value into the instruction itself, because this is where the value is already there. Well, some people in class mentioned that you can use PC because that's somehow initialized. That's a good point. It's possible, but the easier way is to use PC to get an instruction. And the instruction, once it's in the instruction register, now you can use some part of that information to initialize. So I hope you get the point. The point here is immediate is a very desperately needed first mover to allow us to populate the register with values. Once we populate one register with value, we can then go to memory, load the next, load a whole bunch of things into different registers. We can start, but the very beginning, we need something, and immediate offers us that. Here's one example to use an immediate value. The particular example here is a load instruction. Let's say we have a load instruction. We have a destination register, we have a source register, and then what? Well, this is what. We can have a bunch of bits that's used as a value. Okay, the green part is a value. And here's one example in load. Here's another example in an add. This is treated as a number. Okay, so we're not adding the value from two registers. We can use part of the instruction as a value. Of course, we can dictate that that's not an unsigned value, it's a signed value, meaning the highest, the most significant bit represent the sign. So let's say we do that, and we can specify a value. In this case, 1000, it's minus 16. So this add can be differentiated from a different add by saying, okay, that one was adding two registers. So the instruction itself contains only the ID of register. So this means 4 doesn't mean value 4, means the value is in register 4. This is 7 doesn't mean the value is 7. The result is in register 7. But here, this means, let me clean this up. This means one source comes from register R0, but another source is here, right here. It's minus 16. So take the value of R0, add minus 16 to that, put the result into register 010, which is register 2. Okay, that's very convenient. We can do that. And how do we even tell? Please don't treat this as a register. We have to tell the computer. Otherwise, how does the computer know to treat it as a value or a register? And one way to do that is to have a bit. When it's 0, it's not the value, the instructions content doesn't represent an immediate value. So we can call this bit the IE bit if you wish. And we can even dictate for instructions such as load. We will never use two registers. So the source, these couple of bits, even including the I bit, will always be treated as an immediate value. So that's fine. So you see, this is where the early designers of computers have to grapple with. This is what they have to deal with. And they have to come up with, okay, do I do this? Do I do that? How do I set this thing up? And here we're talking about some evolved solution. It's not the very first solution. It's after trial and error, people decided this is a good solution, avoided some of the bad solutions that we tried early. So here's some example, right? The specific encoding here, this doesn't matter. I'm not describing any real instruction set. It's not even the little computer that we're gonna deal with. These are just examples, are contrived examples to show how to have ways of specifying some initial value. Okay, and now are we done? We have initial value. We can do load. Then we can do memory arithmetic operations on them. Are we done? No. Remember, we have the straight line code problem. If we have this, now then the machine is going to start from the first PC execute that instruction, increment the PC by 1, execute that instruction, increment the PC by 1, increment that instruction. And if we repeat that, we're going to execute straight line code. So if we want to do a billion instructions of processing, we have to write a billion instructions. It works, but it's never going to be good enough. It's too slow. So we need some way to change this straight line code model. We have to be able to go back, go forward, to jump across code, because otherwise we're loading straight code from one sequence. And that's the story that we'll continue next week. So this week, okay, there's textbook reading about it. It's that we have finite state machine that can be implemented by sequential logic. And this is really just your combinational logic plus some state stored in memory. Okay? When you store the state in memory, your combinational logic has more input, and the result is a sequential logic. It's no longer a one-shot deal. You can do things one step at a time, and the logical behavior is what we call a finite state machine, and that's cool. That can solve a whole bunch of issues, but we want a computer which is not any finite state machine. It's a much more powerful finite state machine. It's a programmable one. And the way this is done, how do you program a configurable finite state machine? You give it different instructions. And that's why we code. We write, you're going to do this, you're going to do that. And the finite state machine that we call a computer is sort of a meta finite state machine. Its state is actually fairly simple. You describe it in simple sentence. Fetch the next instruction, execute, repeat. That's what the sort of finite state machine, what a computer does in that sense. But the way this is actually done is the way an interesting program is executed has to be broken down into different types of instructions. And we saw some examples. We can have function. We can have ALU instructions or arithmetic instructions, logical instructions. We need memory instructions because we decided register is a good thing. We can improve our encoding, and to ferry data between main memory and your register, we need memory instructions. And this type of system, when you all flushed out, and it's going to be similar to all the computers that we're using, and they're all the same type of a Neumann machine, except the LC3 that we're going to see is much more specific. So that's the topic of next week.